Hi all, good morning. I am Uday Manda, a doctorate degree holder from the University of Central Florida, Orlando. Today I am going to talk about my PhD research work in which I, another PhD student, and my PhD advisor discovered a fourth mode of heat transfer known as piston effect inside a microchannel with carbon dioxide at its near critical condition. The piston effect, also known as adiabatic thermalization, a very rarely investigated and discussed mode of heat transfer. Generally, there are three well-known modes of heat transfer. They are conduction, convection, and radiation. Conduction happens via intermolecular vibrations, collisions, and random motion of molecules. Convection happens via the buoyancy forces or via the bulk motion of the fluid over a hot or a cold surface, and radiation occurs via electromagnetic waves. Out of these three modes, conduction and convection require a medium, while radiation does not require any medium. The critical point of a fluid is defined as the end point of the phase equilibrium curve. Below the critical point, a liquid and its vapor can coexist, but above it, there is no clear distinction between liquid and vapor phases, and the fluid exists in supercritical state. The supercritical fluid may behave like a gas-like and a liquid-like on either side of the Wiedemann line, but there is no clear distinction of phases. The critical point of carbon dioxide is 31.1 degrees Celsius and 7.3773 megapascals. At this point, the specific heat of carbon dioxide shoots up to a very high value. So, the thermal diffusivity, that is the property of the fluid that causes transient conduction, vanishes. Also, in quiescent conditions and in microgravity, such as in space, as there was no active flow, and in the absence of gravity, the convection too vanishes. But from computational fluid dynamics simulations, we found that even in such conditions, the heat transfer occurs via a fourth mode of heat transfer known as the piston effect. In this mode, the fluid that is at its near critical condition adjacent to the hot surface expands and compresses the bulk fluid like an automotive piston. The compression effect raises the temperature of the bulk fluid. This expansion happens because of the sudden decrease in density and a sudden increase in the specific volume of the hot fluid inside the thermal boundary layer adjacent to the hot surface. Also, thermo-acoustic waves emanate from the hot surface, move with the speed of sound, carries heat energy from the hot surface to the bulk fluid. Generally, the fluid that is outside of the thermal boundary layer takes more time to get heated up. But due to the piston effect, the fluid gets heated up very fast. In fact, in microseconds, once the heater is turned on. Our research found that the heat transfer through this piston effect is about 6,400 times faster than that in the conduction mode. Also, from our experiments and simulations, we found that the piston effect is important even in the forced convection and in terrestrial conditions. The piston effect could revolutionize electronics cooling in the future using supercritical carbon dioxide. We published two papers, one in the International Journal of Heat and Mass Transfer and another in the Thermal Science and Engineering Progress. These two publications will provide more discussion of our research in depth. I would like to thank you so much for listening to our research.